Hey guys, I'm Jed. Welcome to my LeetCode review one-take vlog on the 399th problem. Evaluate division. We are given an array of variable pairs, equations, and an array of real numbers, values, where equations of I equals AI and BI, and values of I represent the equation AI divided by BI equals values of I. Each AI or BI is a string that represents a single variable. We are also given some queries, where queries of J equals CJ and DJ represents the jth query, where we must find the answer for CJ divided by DJ. We need to return the answers to all queries. If a single answer cannot be determined, we'll return -1. And let's see the example 1 here. We got input, equations, values, and queries. We need to find such as A divided by C equals 6, and A divided by E equals -1, because E is undefined. Now, let's start with the intuition of this problem. Our idea is to treat the given equations as a graph, where each variable is a node and each equation is a weighted edge. We need to compute the queries, like A divided by C. So we have to find a path from node A to node C and multiply the weights along this path. If a valid path is found, the product of these weights gives us the answer. Otherwise, we just return -1. We can achieve this using graph traverse methods, like depth first search or breadth first search, and even union found approach. Alright, let's start with a depth first search to see how it works. Depth first search, breadth first search, and union found approach. In the code, we start by creating a graph using a hash map, where each key is a variable and the value is another hash map representing neighbors and their weights. Let's say map of string to map of string to double. Let's call it graph. Graph says new hash map. Next, we'll loop over each equation to build the graph with the connections. Let's say for integer I started at 0, I should be less than equations dot size. For each iteration, we'll increment I by 1. And inside the loop, first, we'll get the current equation as a list of strings. Let's say list of string, let's call it equation, gets equations dot get of I. Equations dot get of I. Next, we'll retrieve the dividend and divisor from the first element and the second element of the equation. String dividend gets equations dot get of I, and string of divisor gets equation dot get of 1 here. I'll get 1 here. Equation dot get 0. Then we'll get a corresponding value from the values array. double value gets values of I. Now we'll call the get.putIfAbsent of dividend and a new hash map to ensure that the dividend key exists in the graph. Graph.putIfAbsent of the dividend and a new hash map. Next, we access the dividend's inner map and put a divisor with a given weight into it. Let's say graph.get of dividend dot put with the divisor and the corresponding weight, which is the value. Similarly, we have to add the reverse H by ensuring the divisor key exists, and then we'll add the dividend with the reciprocal weight. And the code is graph.putIfAbsent of the divisor and a new empty hash map. And graph.get of divisor dot put of dividend and 1 divided by value. After building the graph, we need to initialize a results array to hold the answer for each query. Let's create a double array here called results. Gets a new double array with the size of queries dot size. Then we loop over each query and extract the start and ending variables. Finally, we'll process the query accordingly. We'll create a for loop. Let's say integer I started at 0. I should be less than queries dot size. We'll increment I after each iteration. And inside the for loop, first, we need to get the current query from the list. Let's say list of string got query gets queries dot get of I. Then we need to extract the start and ending variable from the query. Let's say string start gets query dot get of 0. String end gets query dot get of 1. Now we have to handle the query with some checks. If the start or the end variable is missing in our graph, we just assign -1 to the result for this query. If not graph that contains key of the start variable, or not graph that contains key of the end variable. If one of the condition is true, we just assign -1. Results of I gets -1.0. Otherwise, If the start and end are the same, we know the result must be 1. So the code is else if start dot equals of end results of I gets positive 1. Finally, if the two variables exist but they're different, we need to perform the depth first search. But before we start the depth first search, we need to create a hash set to keep track of nodes visited during the search to prevent cycles. Let's create a state of string called visited. Get new empty hash set. Then we call the depth first search help method and pass the several parameters. And code is results of I gets depth first search method with start and the product at 1 and visited hash set and the final graph. Finally, after processing all the queries, we'll return the result array, which contains answer for all the queries. The code is return results. Now, let's implement the depth first search help method. Let's say private double depth first search with several variables with several parameters. The first parameter is a string current node. The second is the target node. And third one is the product for this path. And the fourth one is the visited hash set called visited. And the final parameter is hash map, let's say map. Map of string to map of string to double called graph. The very first step inside the depth first search method is to mark the current node as visited by adding it to the visited hash set to prevent cycles in the graph. Visited dot add of current node. Then we need to retrieve all the adjacent variables, let's say neighbors, from the graph. Map of string to double called neighbors gets graph dot get of current. Then we'll check if the target variable is found among the neighbors. If so, we'll immediately return the product multiplied by the age weight. And code is if neighbors dot contains key of target. We'll return product times neighbors dot get of target. Otherwise, if the target is not a direct neighbor, we need to iterate through each neighbor to continue the depth first search. Let's say we create an enhanced for loop. map.entry of string to double, and the variable is called entry. For each entry in the neighbors dot entry set. Inside the loop, we need to get the neighbor node's key at first. Let's say string next gets entry dot get key. Next, we'll check if we have already visited this node during the first search path. If so, we need to skip the loop iteration and move to the next iteration. So the code is if visited dot contains of next. If so, we'll call continues. We'll call continue to the next iteration. Otherwise, we'll call the first search method recursively on the neighbor and update the product by multiplying the current product with the age weight. And code is double result gets first search with next node, target node, product times entry dot get value and visit hash set and graph. After the recursive call returns, we'll check if it found a valid path, which means the result isn't -1. If so, we'll return the result immediately. If result is not equal to -1.0, we just return the result. Finally, after iterating through all the neighbors, if no valid path is found from the current node to the target node, we'll return the -1 as the fallback. -1.0. Okay, that's all of the code. Let's submit our code and check if the solution passes all the test cases. Yes, our code got accepted. Now, let's discuss the time and space complexity. Let's say we'll use the E for the equations, and V for the number of unique variables, and Q for the queries. And the time complexity consists of two factors. The first factor is graph building, because we have iterated through each of the equations once. Inside the loop, we perform the map operations like put if absent, get, and put. And these operations takes big O of 1 time complexity on average. So graph building will need big O of E time complexity. And the second factor is the query processing, because for each query, let's say there are Q, we may perform a depth-first search, and in the worst case, a depth-first search might visit every node. So, and the number of edges in a graph is actually E. Therefore, a single depth first search would take big O of V plus E. And we have Q queries. So the overall time complexity for the query processing is big O of Q times V plus E. This is the second factor, which is query processing. So the overall time complexity, it is big O of E plus Q times V plus E. Then let's get into the space complexity. The space complexity, it is also made up two factors. First is still the graph storage. Because we have stored the graph in a nested hash map. And in the worst case, we might have V nodes. The total number of edges we'll store is E. So the space needed for the adjacency list is related to the number of nodes and the number of edges. So the overall graph takes like big O of V plus E. V plus E. And the second one is the depth first search method, helper method. Because for each depth first search call, we'll use the weighted hash set. And in the worst case, it could store all the nodes, which will be big O of V. So the overall space complexity, it is big O of V plus E. And this is the end of my LeetCode review one-take blog on this problem. And I highly recommend you guys to visit my online GitHub page here. You can see all the problem description, intuition, an idea, and all the solutions. For example, you can see the detail for breadth first search and the union found approach here. And for each approach, you can see all the code with detailed analysis and the final time and space complexity. You can also visit my GitHub repository here, which contains all the codes and nodes to build this online GitHub page. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.